All right, this is actually going to be the last lecture for the semester. The plan is to have our last exam of the semester on linear algebra, and then Octave MATLAB will be on this exam too, and that will be on Monday. Today I want to cover, actually we're not going to look at all of the topics mentioned on this slide. I want to look just at probability and statistics. I'll briefly mention data structures. I'm not going to actually go into any depth, and I won't assign any homework problems on data structures. And then I want to look at images and animation also. So there are a number of different functions you can use available in MATLAB and Octave for generating random data with different distributions. So the most basic function is rand, which when called by itself actually just generates a random number between 0 and 1 every time you call it. Okay. Well, typically you may want to call it, if you pass it 2 arguments, it returns a set of random numbers, an array of random numbers, or a matrix of random numbers. 2 by 2. Originally here I got a 10 by 1 vector, so this would be a data set. All the numbers here are uniformly distributed between 0 and then up to 1, and then rand2 would um, return a 2 by 2 matrix with all the numbers distributed between 0 and 1. If you want to generate random numbers between, let's say, 0 up to 100. So this is rand goes from 0 just under 1. It will never return 1. It can actually return 0, but it will return a number between 0 and 1, 0 inclusive. So this would generate a set of random numbers between 0 and just under 100, continuous random variable. Okay, and then we could plot a histogram of that. There are a couple different histogram functions. His C actually returns basic histogram functions, does histograms with the bins centered at the given vector. His C would produce a histogram with the edges at the numbers in the vector. Here, his C won't actually produce a plot in this case. Since we have a return argument, instead of producing a plot, it just actually returns the number of values within each bin, and then we can use the bar figure to produce the histogram. And alternatively, you could just produce it directly with his-C. This is just just showing something a little different. So here is that slide. Here I show the results on 2 separate graphs, 2 separate figure windows. So that's what the first figure window looks like, and this is what the bar window looks like. Now it's important to realize that every time I run this, I will get a slightly different set of numbers, and the figures will change slightly. So that's because it returns a different set of random numbers every time I call the rand function. But again, theoretically, the numbers here should be uniformly distributed between 0 up to just below 100. Okay. Some other functions that are available in addition to the basic rand function. You can use rand_n, which will draw numbers from a standard normal distribution. So with a mean of 0 and a standard deviation of 1. You can use the random function to generate random numbers from many more distributions. And actually what Octave and MATLAB have done is actually they have now included a bunch of other specific functions there's uniform random, uniform discrete random. So this would be like for a card simulation. You can set this up to return the numbers from 1 to 6. Normal random, you can pass in, it takes arguments of the mean and standard deviation. Binomial random number generation, exponential, hypergeometric, and on and on and on. Okay. Now, some cases you want to actually every time you run the simulation, produce the same set of random numbers. You can do that by seeding the random number. In that case, you seed it with a particular value and at the beginning of your script, and then in that case, every time you would get the same set of random numbers. And this can be useful when you're debugging or want to make sure that you produce the same output every time. So what do you do with the rand function if you want a random number, other than with a uniformly distributed number that's has a different range than 0 to 1? Well, again, there are now in modern releases of Octave and MATLAB, you could use the uniform frand function to generate those distributions. With older versions of MATLAB and Octave, what you could do is take the number that's 0 to 1, multiply it by 10. This would give you a number that's then between 0 and 10. And if you add 5, you get y now is going to be, all the numbers in y are going to be distributed between then 5 and 15. 0 to 10, we add 5, so the number would be between 0 and 15. If you want to generate uniformly distributed just integers, okay, so in this case between they would be between 6 and 15. What you can do is multiply the random number generator here, which again produces numbers between 0 and just up to 1, multiply by 10. So this would give you numbers from 0 just up to 10, add 6, and then this would give you numbers between 0 and just up to 16, just below 16. So if you floor that, we'll get uniformly distributed numbers between 6 and 15 in this case. You want to use floor here instead of round, because if you look just at the first part here, between 0 and 10, if you round, it's just the numbers between 0 and a half that would be rounded to 0, and so you don't actually get a uniform distribution in that case. But and there's some tricks you can play so that you can make sure that you get that uniform distribution. But this kind of the standard method is to actually use floor here, or you could alternatively use ceil to get numbers that would be between 7 and 16 in that case. So let's see. This rand-n generates normally distributed random variables with by default with a mean of 0 and a standard deviation of 1. But if you multiply those by a number, that changes the standard deviation by that number. So if we multiply y by 5, we get a standard deviation of 5, and then if we add 8, that would actually change the mean. So I've got the numbers here on this slide, and I'm showing them in actually a subplot on the same figure so that we can compare them. So here is the first set with I use the same axis values so that you can compare the width instead of letting Octave auto scale this axis. But you can see here we've got this classic kind of bell shape centered at 0 and with a narrow width. Standard deviation of 1 in this case. Here I changed the standard deviation so of y2, so it has standard deviation of 5, and you can see the center value appears to be 8, consistent with the math on this slide. Okay. So this exercise is simulation and Brownian motion, where you start a particle off at position 0, and then it moves either left or right 1 step, and then we're going to have it go through 10,000 steps. Here in the exercise, they actually have you produce a histogram of all the positions. That's not normally how you would produce a histogram, because this is a histogram of the position at different times. In my opinion, what you'd really want to do in this case is actually plot the data to show the position as time. But again, here with this simulation, this is the histogram that it asks for. And this is a plot of the position. It's always going to start at position 0 and then move left or right 1 step. And we see after 10,000 iterations, the particle that's subject to Brownian motion in this case, what is that, is around 140 steps away. Again, every time I run this, I'm going to see a different figure, always starting at 0, here at 150. It could just as well in one run end up at a negative position, like actually this next run. So here it oscillates around 0 quite a bit, and then kind of at the end, the last 1,000 or so steps, it actually starts to very negative. And if you look at the histogram, you can see by and large most of the steps are positive, consistent with this graph. It's only at the very end that it actually goes negative, but it does end up at a negative position. Okay. Let's see. So here's the author's solution. Okay, I'm not really going to cover data structures. So our basic data element or data type that we've worked with is just a matrix, or as a special case of that n by n matrix is an n by 1 vector or a 1 by 1 scalar. And again, we've seen that it can be complex. But that's really all all that we're going to work with, or that I expect you to work with in this course. Just be aware that Octave and MATLAB do support a couple of other types of data structures. Here in the slides, it mentions what are known as cell arrays and also structs. Cell arrays actually can hold any type of data. So with our matrix, they all have to be numbers essentially. Well, cell arrays can actually hold strings, they can hold scalars, they can hold vectors, they can hold matrices of different sizes, they can hold other cell arrays even, they can hold structs. So any of the available data types in MATLAB you can put in a cell array. So sometimes there's a need for a data container like that. If you want something that holds a person's name as well as maybe their phone number, social security number, you could use a cell array there to hold both of those in one row of the cell array, for example. Struct is similar, except for a struct, you have corresponding names for each of the elements in a struct. I'll show just a quick example. So this is looking at cell arrays first. Here's a 3 by 3 matrix. Here's a 3 by 3 cell array where we can store names, numbers, or even vectors, or the empty matrix. A struct, you would construct a variable, in this case it's s, and then to add corresponding values, you have to add fields to the struct. And these can be anything you want: s.name, s.age, s.gender, s.scores, to hold a vector. You see here that a struct can also hold different data types, and strings and or arrays or matrices. You can actually have arrays of structs. So again, another application would be something like a phone book application, where you have a name and then the corresponding phone number or social security number for each of the elements in the struct array. And I think that's when structs actually become much more useful, is when you actually work with struct arrays. But I'm not going to cover those. I'm not going to assign any homework on them. I just wanted to mention that they are available. In addition, Octave and MATLAB also have a map data type. That's another type of container for holding index values. When we come back, I want to look at some advanced graphics, producing images and animation, but I want to take a little break here.